Calc BC, Unit 4, Day 7 lesson. So we're now going to talk about polar integrals, what we can use them for, how to do them. And today's homework is going to be pretty much just more integration review, just to get you ready. And our next day we'll really start making you do some of these. But let's try and figure out what's going on here. So we're going to go and just use a simple example, polar curve, that's a cardioid. Did a quick table. It should be sort of horizontal in nature, orientation. It's going to be 2, 1, 0, 1, 2. Okay, so 0, 2 is right here. Pi over 2, 1's here. Pi 0 is here. 3 pi over 2, 1's there. So this is what it looks like. Now, what we want to do is we want to talk about how could we find the area inside one of these shapes. We've done area between lines before, generally not, So, these shapes usually are kind of closed, and so we can try and find the area of a polar curve. What we're going to do is we're going to look at the slices. Now, the way these are graphed are in a sort of a radial fashion. So it's being graphed like this, right? As we go, you're getting, as the angles, go, we're getting new points. Now, we also want to slice it like that as far as area. So we're going to take one of these slices, okay, and we're going to say that the angle is d theta. So one slice looks like this. Now, it looks like a sector. It's technically not a sector unless the shape happened to be a circle centered at the origin, which is a rare case of polar curve. But it's close to a sector. Kind of like when we sliced Cartesian graphs, rectangular, with vertical slices, horizontal slices. We said, well, it's like, let's use rectangles, thin rectangles. And even though technically it didn't fit perfectly, it was close enough. If we made them smaller and smaller, the error got less and less. So in this case, instead of using rectangles, let's use sort of a triangular sector piece of pie. Now, back from geometry, how would we find the area of a sector, like a legitimate sector? And it came from this idea that the area of the sector, that piece of pie, over the area of the whole circle, would be the same as the angle in the sector over the angle around the whole circle, would actually be the same as the length of the arc associated with that sector over the length of the arc around the whole circle, which would be 2 pi r. This is basic relationship that all these different things are proportional. The area, the angle, the arc length are the same fraction of the entire area, the entire angle, the entire arc length. Okay, so from this, we could solve for the area of the sector is theta over 2 pi times the area of the circle, right? We're not using this. I just threw that in there just to remind you. We're using this. We're solving for this. We multiply both sides by the area of the circle. Now, that's going to be theta over 2 pi. Now, the area of a circle is pi r squared. Now, this is, of course, we're using angles and radians, which works out a lot nicer. The pi's cancel, and we get 1/2 r squared theta if we kind of just clean things up and move things around. So the area of a single sector is 1/2 r squared theta. So the area of one slice is going to be 1/2 r squared d theta. All right, so it's not that crazy. We use a little simple geometry, got the area of a sector. We're going to say each slice is really close to a sector, so let's use that as the area of it. Okay, now we want to accumulate all the slices. So we're going to integrate, and we'll probably just move the 1/2 in front. You don't have to. And this is the formula for the area inside a polar curve. And we're going to memorize this, but it actually was not that crazy of a derivation. It was a couple steps away from geometry and a little other calculus thought, slicing things up into infinitely thin slices. So that's what we're going to be using, 1/2 r squared d theta. And that comes from this geometry relationship. So the area of this shape, we could do a quick sketch. It's cardioid. Cosine 0 is 1, so it's going to be 0, 1, 2, 1, 0. So it's going to be bigger to the left side. It's definitely going to be a left-right kind of horizontal oriented graph. All right, so 0, 0, pi over 2, 1, pi 2, 3 pi over 2, 1. So cardioid looks kind of like that. Okay. Now, so if we want to find the area of it, we just developed the formula for it. This is the area of 1/2 r squared d theta. So for us, it'd be 1/2, and the radius is 1 minus cosine theta squared d theta. Now, the limits are going to be what it would take to create the whole shape. So cardioids and limacons are 0 to 2 pi. The circles are usually 0 to pi. And some of the rose curves are 0 to 2 pi, some are 0 to pi. So you just have to be, paying attention to what the limit should be. And so that's how we're going to find it. Now, there are other ways that you could set this up. You could use symmetry, which often, whether you like it or not, they like to use these on the AP test multiple choice questions when they say, well, find the area of this shape, and then all the answers are setups of integrals, and then you don't actually find the final answer. They like to use symmetry a lot, and sometimes that can make the work easier. So instead of doing the whole shape, we could do half the shape, 0 to pi, and then just double it, right? So we could do 2 times 1/2 0 to pi of 1 minus cosine theta squared d theta. And then one of the nice things is the 2's cancel out. A lot of times it gives you nicer limits to plug in, not so much in this case, but in other ones. Now, if we're going to actually go ahead and integrate this, then I think what we're going to need to do is actually FOIL this out. 1 minus 2 cosine theta plus cosine squared theta. Okay, definitely need parentheses around all that. Now, here's the deal. Integrating 1, easy. Integrating 2 cosine theta, easy. Integrating cosine squared, that's a problem. That's not straightforward. So what we need to do is we got to get rid of the cosine squared. And what we're going to do is we're going to use some trig identities to manipulate anytime. A lot of times when you're finding the area of a polar curve, it's going to give you a cosine squared or a sine squared, because usually the r's have cosines or sines and it gets squared. And this is a common problem on these particular integrals. So we're going to do, I have a lot of stuff written down here just to kind of help, but you're going to try and follow along, and then we're going to just kind of memorize the outcome of this. Now, these are the sine and cosine angle addition trig identities, which I think I brought up on a recent assignment, a couple assignments ago. The double angle ones come from those. So if it's x plus y and it's double 2x, it's going to be x plus x. And it'd be sine x, cosine x, cosine x, sine x. And then you add them together and you get this. So that's sort of like the outcome of the doubling for sine. The doubling for cosine, it's going to be cosine x, cosine x, sine x, sine x, but it's the opposite sign. If it's plus here, it's minus here. So there's the double angle for cosine. Now we're going to use another trig identity, the Pythagorean trig identity that says sine squared plus cosine squared equals 1, so that we can rewrite. We're going to actually focus on the double angle for cosine is the only one we're going to really need consistently on these problems. So we're going to replace, so we're going to take this and we're going to replace sine squared with 1 minus cosine squared, and then distribute the negative, and then this is what you get. Or the other version is you replace cosine squared with 1 minus sine squared, and you get 1 minus 2 sine. So we're going to use both of these. And then what you're going to do is you're going to solve for cosine squared. So you're going to add 1 and divide by 2. In this case, you're going to subtract 1 and divide by -2. Okay, and this is what you get. Now, I'll probably say that I'll probably always write them like this. So this is really just a bunch of trig identities so that you can replace cosine squared with something that does involve trig squared, or sine squared with something that does involve trig squared. They both make use of the cosine double angle identity. And this is what you get. The nice thing is they're both almost the same. They both involve cosine. So when you do sine squared, don't put sine 2x here. The only difference is the sign has a minus. That's it. So you're going to memorize these because we're going to use this a lot, and you don't want to rederive it every time. That's pain. You guys should have been able to follow that derivation, just a bunch of trig stuff that you could have done back in like algebra 2. But we're going to use one of these often on these integrals. So in this case, we're going to replace the cosine squared with 1/2 plus 1/2 cosine 2 theta. Now it's a double angle identity, so whatever angle's inside here, you got to double. This time it was very simple, but sometimes there's like a 3 theta inside, and so that would be a 6 theta. And then we could, so now we can integrate this. You could combine the 1 and the 1/2 into a 3/2 right away, or you could wait. The antiderivative, or integrating with respect to theta, is going to be theta minus 2 sine theta plus 1/2 theta plus 1/4 sine 2 theta. Those are the antiderivatives. And this is a definite integral, so we're going to be plugging in 0 to pi. And so in the next step, we could combine the 1 theta and the 1/2 theta to be 3/2 theta. Put pi in. Minus 2 times sine of pi is 0. Plus 1/4 of sine of pi is 0. Then we got to plug the bottom limit in. 3/2 times 0 minus 2 times 0. Sine of 0 is 0. Plus 1/4 sine of 0 is 0. So all these 0 terms drop out, and the answer for the area inside that cardioid is 3 pi over 2. I mean, surprisingly nice. That's it. That's how we do it. So we're going to be using these identities quite a bit. On tonight's homework, that's it for the notes. And tonight's homework is really just more integration review. And then you will get some problems on the back that start to have some more of this trig stuff inside. And you're going to need to use that trig identity for some of them. And only really the last problem, you're going to be setting up completely on your own and finding the answer completely on your own. The other ones are set up for you, and they aren't necessarily tied to a particular polar function, but they involve the work that we're going to be doing a lot of. So this is really kind of like easing our way into it. Okay, so try all these problems, and let's get really good at integrating with trig